Hello, I'm going to give you some pointers for developing with freeRTOS and an STM32 Cortex M3 in my case, but with M4 should be the same, using Eclipse Neon. Actually, I collected a lot of information from different places in the web, and just to maybe spare you some of the difficulties in finding all the information, I will just dump what I learned so far. So just to set a little bit the context, I'm using a cheap development board based on an STM32 F103C8, and it is a board like this one. You can get them very cheap. We're talking about $4 or $5 delivered normally. Be aware they do not include JTAG interface. So you need to have your own JTAG interface. See, this is the JTAG connector, right? And it doesn't have a JTAG chip on board, right? So it's not like an Arduino that you plug it in and then you have everything. You need to have a JTAG programmer and debugger. So anyway, this microprocessor, this MCU, can run on 72 megahertz. It does have some interesting features, and just to play a little bit around with Cortex M3, it's a good option. Also because, as I said, they come very, very cheap. Okay, so basically, this is the specific MCU that I have on the board. There are some variation, but this is quite a common one. The IDE that I'm using is Eclipse Neon. I like Eclipse because I'm using it for other languages as well, so to me it makes sense, just to have everything under one single IDE. And obviously you need to install the toolchain. That was a bit painful, honestly, but you find all the information here to install the toolchain. I did have an issue with the make. Didn't really work, the standard GNU make, so I had to install a different one. If you look in the web, if you have the same issues, that there are some alternative solution based on Chicwin, and it worked for me. As I said, I have a JTAG interface. In my case, I'm using a Seger J-Link. They used to be a bit expensive. Now they dropped the prices. I think after there was a kind of invasion of Chinese clones. But there are alternatives that are even cheaper than that. However, this one works nicely for me, so I'm happy with that. I'm using STM32CubeMX. That's the tool that is made available graciously by ST Micro Devices, and it allows you to configure your environment, your MCU, and all the libraries that the peripherals that you want to add in your project. Unfortunately, what happens is that when you create the code in STM32Cube, it doesn't create a project for Eclipse. It does create some code that then you have to import into Eclipse. The problem there is that it's a little bit less than straightforward. So I found this nice Python script that automates all the process for you. So that's really helpful. It helps a lot, at least in my case. So we've we can go immediately to STM32Cube, and the idea is that I wanted to create a project using freeRTOS. That's an option. You're not, it's not mandatory to do that, but I wanted to play with freeRTOS. So here with STM32CubeMX, you can have it as a standalone application or as an Eclipse plugin. Actually, it doesn't change anything. It is exactly the same application, and it's not that if you run it through Eclipse directly, it will generate the code in an Eclipse project. It will still be somewhere in your hard disk, and then you will have to import the code. So there's no real advantage to me. I don't see any kind of advantage of using the plugin instead of the standalone application. Anyway, you create a new project. First thing, you have to select the MCU that you have. You select the family. That's fairly easy. In my case, it's an F1. so before it was F103, so that's the family. The line you will see 103, and then you still have to select the package. In my case, I know it should be a 48 pins, and in fact you see the C8, there it is. So I select it, double click, and that gives me, this is I'm not going into the details of STM32Cube, but there are some videos on the web and YouTube that you can find. They're quite detailed and pretty good. But the idea is that here, first of all, I want to use freeRTOS, so I just enable here in the middleware. It's kind of convenient. I will automatically include the freeRTOS part that is needed in our project. And then let's say that I want to have I don't know, the clock. I want to, yes, no, sorry, this is the real time. I just wanted the RCC instead. Let me, okay, I want to enable the external crystal, and let me show you. This is the board that I have. You see there is an external crystal here. So if you have that, you can use an external clock source. It's a bit more precise than, well, a lot more precise than the internal oscillator. So if you have it, it's a good idea. And you see automatically those pins that are marked in green, because they say, if you want to use an external crystal, then it means that it is connected to those pins, and those pins, they cannot be used for anything else than the crystal at this point, right? So you can also enable master clock output. You see here, that means that you can basically have normally a divided value of the clock as an output in this pin, and then you can measure it if you need, or if maybe you need to change some other devices. That's up to you, right? Then what I will say is that there is one thing that I discovered. When you use freeRTOS, actually you cannot only use the system tick, that means the hardware clock here, but you also need to, for some reason that I'm not really sure, you need to set also a timer clock, and then should be like this, I guess. It worked for me before. And the idea is that clock configuration can be a bit complex, but however, the Cube, STM32Cube helps a lot, because here, you see, you just go here and say, you know, I want an output clock of 72 megahertz, which is the maximum. And then say, hey, your parameters, they're not really good for a 72 megahertz. Do you want me to fix them? And yeah, thank you very much. And then it does it, right? So I will show you here. I didn't enable, I disabled finally the master clock output. I will show you something. If I go back here and I say, I also want the master clock output, then I go here in clock configuration and say, hey, watch out, because, well, I already clicked OK, but 72 megahertz was too high. So basically it divided by 2 because it cannot output such a high frequency, right? So automatically it finds the solutions for you. That really helps a lot, honestly, right? So, and then you add the other peripherals that you want. You really need to think ahead which kind of peripherals you need, because going back and forth here in adding things after you already imported code in your project might not be the easiest thing to do. So you should plan ahead and say maybe you want to have a UART, and then this thing is in red. The reason why it is in red, because we're using the we'll show you the master clock output, and as you can see, if I disable it now, it's not in red anymore. Why? Because actually it's using the same pin for some functionality. So if you enable the master clock output, then you are preventing some other functionalities. I don't need a flow control, so I will leave it like this. And that's pretty much it. I'm saying maybe you want to add an ADC, or you know, how many channels, and automatically you will see those pins are allocated to the ADC channels, right? So again, since we added serial port and stuff like this, then the clock has to be changed a little bit because it has to fit some specific needs for the peripherals. So the good thing is, you know, it says I can do that for you. Now the problem is, you see, it went back to 56 megahertz, and we don't want that. We want to force it to 72, so you have to find some kind of combination that still works, and apparently we were lucky. There is a viable combination. I'm not going into the detail of this. Here you can change basically the clock source as an external crystal. You can change the PLL. You can change, this is the PLL multiplier. You can change the divider. You can change different dividers at different levels to have the values that you need. But the good thing is the system, the STM32Cube, does it for you. So you don't need to really worry about that. It's good to understand what's happening here, because at least you know, you see which kind of solution it's finding and does it still meet your requirements. So you should be able at least to understand what's here. So then you have some kind of configuration here. For my example, I don't need to change basically anything, but every module can has a number of parameters that you can configure it. So if you know the module itself, if you know the functionality that you need, then it's quite simple. For instance, what we can say is that for a UART you might want to have NVIC. There it is. You can enable the an interrupt for the UART. Normally that should be taken care of from the freeRTOS. Anyway, here you can specify the baud rate, and so it will generate automatically the clock configuration for you, also to achieve the correct baud rate and everything. So without further ado, here you can go and we can generate code, right? I have kind of folder where I put all this kind of projects, and then we call it freeRTOS test 2, and it will generate the code. Yeah, there it is. This is the thing that I'm not really sure, but it's telling me that I shouldn't use the hardware clock when I'm using freeRTOS. It's something basically that I managed here somewhere. Where was that? I don't know how I did it, but it worked before. Let me check if that was the case. Nope. It is RCC. No, this is correct. This we don't need it. Well, forget that one. It was just for an example. And debug. Obviously, we want to have JTAG debug. There it is. Time-based source will be timer 1. Timer 1. Why did? Because we used it for another thing. Let's disable this thing 1 second, and we say timer 1. Okay, now it's used for the time base of the freeRTOS basically. So if we now try to generate the code again, you see that message is not coming back anymore, and then you know all the code is generated in this folder. We don't need to open that folder now. What we do is we just go here. Well, first of all, we go to our Eclipse and we create a new project. File, new, C project, and we use the cross-arm GCC. In my case, we call it freeRTOS test 2, and we add the family that matches our device. Next, it is a medium density. That's the case of the 103C8, and those parameters are correct. And you have to check those parameters basically on the ST website for your specific device. You will find the correct parameters. Here we leave it as default, there's no need to do anything, and then we go next. This is the toolchain that we are going to use. That's also fine. We go finish, and the project is created, right? But it doesn't include yet whatever we did before with the CubeMX. So basically, using the Python tool now, we just specify the source, the target project here. It's the one that we created in Eclipse, and the source where basically we deployed the CubeMX files. What's wrong? Correct. There's one important thing that's that I forgot. You see, in the settings you have to specify the toolchain ID, and you have to put it as a SW4 STM32. Okay, then yeah, warning, we're happy. Generate code again, close, and then let me see. I think there's some wrong path here. freeRTOS test 2 CMC and cube projects. freeRTOS. Let me see if the path is correct. The CMCs STM32 cube projects freeRTOS test 2. freeRTOS. Well, it's not case sensitive because I'm using a Windows machine. Obviously, if you're using Linux, you need to be a bit more careful. Well, now apparently the project was imported, so we go back to our Eclipse Neon, and this is our project. We just refresh with an F5, and normally you see you also have middlewares now. You have third party and freeRTOS. So basically it was automatically added by the CubeMX and then imported using the script, right? It's not too complex if you use the script and this kind of now what we do is we already have the main.c open, and it already works. Basically it creates a skeleton for freeRTOS application, and this skeleton already contains one task which is empty. It's not doing anything basically. So where is it, our task? Let's find it. It is it already added the UART init and everything because we asked to STM32 to also include the UART, right? So whatever peripheral that you add, then automatically it will be added here. Okay, this is our task. Basically, you see it is empty. It is it loops forever. This is the way that tasks work in the operating system, and it includes delay. Delays are in milliseconds, so we'll put like 1 second delay, and then printf, let's just say either only task exclamation point, right? So basically we added something should be done and will be here in the console later on, hopefully, if it works, you know. And there's already the code needed to set up and to run this task because it's part of the skeleton. It's here. Okay, so we'll get into the details later. Let's just compile and see if it works first, right? So we go project, we go build all. It's building. Finger crossed. Yeah, it seems it worked. Now the second thing we have to do is that we have to configure our debugger. My interface is already connected, and it is the J-Link is connected already to the development board. So here we can go as debug as, we select debugger configuration, and you see here in my case I'm using the Seger J-Link GDB server. So I add configuration here, and then the debugger will already have the parameters that are already configured for my J-Link, and here it's already pointing to the correct elf. We can check if it is correct. Yes, it is not this one, but it is freeRTOS 2 debug, and you see after you have the build, after you build the project, then you also have this file, and it can be used for debug. So from here we can go and we say debug, yeah, save, no problem. So we are in the debug interface. It was basically here you see well, a lot of text, but basically it went, it did erase what was in the flash before, it programmed the flash, it verified it worked, and then basically now the freeRTOS and our application are ready to run in the device. So we start the debugging, and what we do is nothing has happened here apparently. Starting target CPU. Let me see. Let's pause and let's see. Stop. Okay, we stopped. Here normally I was expecting the, let's go back 1 second to the C++. There it is. Well, I just put also /n so that we have something. Printf, this is the already executed. Project build all. And we go here, debug as. Our debug configuration is already there now. We just need to run it. It will upload again. We run the application now. You see, I am a task. So basically, what's happening is that the skeleton that we created, right? That we filled actually, the skeleton that we used to send a string to the task, is every second, because we have a delay here, we start the task, and then the handler, where is it? Here, right? It goes, hi there, I'm a task, and then it delays for 1 second. Now, what if we want to create another task? Well, I'm glad you asked. Let's stop this one, and we go back to our C++. So the point is, and I know maybe I'm a bit stupid, but it took me a little bit to figure this out. Actually, these things, they are macros, they are not functions. Why this is important? Because the tricky thing is that I never found anywhere this default task where it was defined, right? This is the procedure that we saw before and that we use to generate our output on the console, right? So that does exist, but again, this one was not declared anywhere. Well, it works because this one is a macro. So let's just say that we want to create a second task that we call my task 2, for instance, right? So we copy those 2 lines, and we see here we create a name, and it's gonna be my task number 2, and here will be start my task 2, right? And here is my task 2 again, right? So, and also this one, this handle will be my task 2 handle, right? So now we need to do 2 things. This has to be defined, okay? So normally we can copy the other one, which is on top. You see, it's called as an operating system thread ID, and we call it my task 2 handle, right? And also we will create a function below that is actually executing the code. So start my task 2. Okay, so let's go. We take this function here, we copy it and we modify it, and then we run this one like every 2 seconds. I am another task, and this one is gonna be start my task 2, right? So basically, let me check, but I think we are all set. Yeah, so you see this is the new function, the procedure that it's running, the code of the task itself. We did set the same priority. This is the stack size. You can check the freeRTOS documentation for that. I just left it as default as for the skeleton. And then it means that we have this handle that we defined, and then this thing will actually create a thread, and this will be based on our task 2 that was created here. So we just build project, right? I think it's already done. Yes, it looks like. And now we go as debug configuration, debug. Yeah, save it. Ooh, no, there's something wrong. Good. What did we do wrong? My task. Yeah, that's correct. I hate these colors. I have to change this. My task to handle. Yeah, that seems quite reasonable. Save project, build the project, and then again debug as where is it? Here. Debug. It worked. Now we run the debugging. You see now every 2 seconds I am another task, and every second you see I am a task. So basically we added another task in in our application. So we stop it here, we go back to the C++, and the idea is that eventually you see those task procedures. Let me just jump here. They can also send and receive data from queues. You can create a queue, and then you can use the queue, for instance, from this task to send a value to this other task. And the idea is that you don't need to schedule this task anymore, because it will be automatically scheduled by the system when it's waiting for the value in the queue. But this is basically where I'm at. So I hope this is helpful also for you. Thank you. Bye bye.